Welcome to Lab Chemistry, the final chapter. This chapter is chapter 11 in your textbook, page 340. This is the perfect chapter to end our year with. It has a lot of interesting topics, some fun demos and labs, and lots of real-world STEM connections. Hope you enjoy. There will be three main topics discussed in chapter 11. I'll be taking care of pressure. Mr. Lowry is going to teach you about temperature, and then we'll split up the gas laws between the two of us. Pressure is defined as the force per unit area on a surface. Mathematically, it's defined as P equals F over A. Pressure equals force divided by area. A perfect example of the relationship between pressure, force, and area is a ballet dancer. Because force is constant, the ballet dancer's weight stays the same. The pressure the ballet dancer exerts against the floor depends on the area of contact. In the first diagram, the area of contact is very large. She is standing flat-footed, and so therefore the pressure exerted is very low. As you move across the diagram, the area of contact starts to decrease. In the final diagram, the area of contact is very small, and you can see the pressure increases significantly. The smaller the area of contact, the greater the pressure. A great example of this pressure relationship is a bed of nails. Here's a short video showing you a bed of nails on the Ellen Show.
Really, when you think of pressure, you think of like weather or something like that, but pressure can be defined a different way. And pressure is when two things come in contact with each other. So here, hang on to the balloon, and a balloon loves a nail. So we can define pressure this way. So kind of watch this. So see how the tip is right there? All the pressure is at that point right there, and then we get a pop, right? And that's fun. Did you like that?
No.
No, okay. That is not fun. So that's why I'm not using a nail at all. My great friends at the Arizona Science Center loaned me this. Look, it's a little bed that's here, and there's 4,538 holes. And in those holes are this. Look, there's 4,538 nails. So in theory, this should be really awesome, okay? If you can take the pressure and distribute it over the entire table like this, it should be fine. And here, for example, watch. Take an apple and just kind of drop it on the nails, and you'll see that it bounces kind of right off. But that's okay. Your flesh is thicker than this, all right? So it is not a problem. That was silly right there. This is pretty. So what I was thinking was, if you're up for it, I got you this nice little pillow. And then I was just kind of thinking, I'll help you if you just kind of want to lay down on this, and then I'll show you the next part. It's fine. It's clean. You want to? Here we go. 4,538 nails. Your body. Isn't that cool? Are you okay?
Yes.
I can't make it go down, but the up part was awesome. All right. I think we're going to be just fine.
And you can feel how sharp they are, like on my hands.
Sorry, but it's distributed across your entire body. So if you just lay on one nail, you would ruin the weekend. But you lay on 1,000 and you're fine.
Like if I went to sit up right now, it would be bad.
No, you don't want to sit up. All right. So watch this. It kind of comes back down again, and you are perfectly fine. You can take a tremendous.
There's one of those bed of nails down at the Science Center in Pittsburgh as well. Gas pressure is caused by collisions of the gas molecules with each other and with the surfaces with which they come into contact. Now we have an atmosphere surrounding the Earth, and this shell of air molecules surrounding the planet collides with the Earth's surface to create pressure. We call it atmospheric pressure. Check out this short video talking about how heavy the air is.
You may not realize it, but from the moment you got out of bed today to the point where you sat down to watch this video, you've essentially been swimming. Why? Because air is a fluid just like water. It has waves and eddies, it flows, and when you push air out of the way, it rushes around you into a wake. So why don't we notice it most of the time? We commonly think of air as empty space. But while 1 cubic centimeter of interstellar space, the volume in the tip of your pinky finger, contains roughly 1 atom, the same volume of air has about 10 quintillion molecules. If that sounds hard to wrap your head around, it happens to be about the same as the number of insects alive on the planet, all crawling, climbing, and flying over each other in an enormous, tightly packed swarm. When this swarm of molecules runs into things, it exerts a force, pressing against the boundaries of the fluid like water pressing against the glass of a bottle. This is known as air pressure. And while air is lighter than water, all those molecules still get pretty heavy, with the total air filling a typical school gym weighing about as much as an adult elephant. So when you walk into a gym, how come you're not immediately crushed by the elephant of air in the room? Well, first of all, because most of it is pressing on the floor and the walls, and the part that is pressing on you is pushed back by the pressure inside you. You see, the air, as well as the water and everything else that fills our bodies, exerts an amount of pressure equal to that of the air outside. Of course, this is no accident. It's precisely what allows us to survive in the normal atmosphere, and what makes it more difficult at high altitudes or deep water. And we normally don't feel the air pressing on us because it's generally uniform. So even though different amounts of air molecules are hitting you at different times, the swarm is so thick that all those little differences average out. What happens when air pressure isn't uniform? This means that the molecules are pushing harder in one region of air than another, driving the airflow from the higher pressure region to the lower. We feel this flow directly as wind, and the pressure systems that meteorologists are always going on about are responsible for other weather changes, from the mundane to the catastrophic. But differences in air pressure do more than just let us complain about the weather. They're the very reason we're alive. We breathe by lowering the pressure in our lungs, allowing air to rush in. So the next time you take a deep breath, think of the unfathomable number of air molecules you're commanding to move. We look up at the night sky to ponder the infinity of space. But unless you're watching this video from that deep space, there are more air molecules in and around your body than there are grains of sand in all the world's beaches and deserts, stars in the visible universe, or both of those numbers combined. The vastness of the universe is right in front of you and inside you.
There's some really interesting demonstrations that Mr. Lowry and I will show you revolving around atmospheric pressure, so something to look forward to. As you can continue throughout this chapter, you'll learn that the pressure of a gas depends on many different variables. We'll be talking about temperature, the volume of the gas, and also the number of gas molecules. A barometer is a piece of equipment that allows us to measure atmospheric pressure. Here's one last short video showing you how a barometer works.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, The idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
There's going to be some different pressure units that we use in this class, and we'll have to learn how to convert between them. In the barometers that we just watched the video about, usually you're going to measure that in millimeters of mercury, mmHg, or sometimes that's in inches of mercury. For very, very high pressures, we use the unit of the atmosphere, the ATM. The Earth's atmosphere at sea level is set as 1. So if you're talking about a planet that has a 60 atmosphere pressure, you would know immediately it's 60 times that of the pressure on the Earth. Atmospheres can also be used for scuba diving applications. The Pascal is the metric system or SI system unit, named after Blaise Pascal, who was discussed in that short video. In our situation for chemistry, we will normally use the kilopascal. There are 1,000 pascals in 1 kilopascal. And then in the United States, we use the English system measurements, and that is going to be in pounds per square inch, or PSI, for pressure. For pressure conversions, you'll use the factor label method, or what some teachers call the conversion grid method. Here's the pressure conversion factor. All of these units are equivalent. 1 atmosphere equals 14.7 pounds per square inch. That equals 760 millimeters of mercury, which is also known as torr, and that's equivalent to 101.325 kilopascals. Those are all equivalent to the pressure, the atmospheric pressure of the Earth at sea level. In your next lesson, you'll learn how to convert between the different units of pressure and gain some practice with this technique. Good luck.